It's my pleasure today to introduce Dr. Sören Keller. And Dr. Sören Keller joins us today from the Helmholtz Centrum from Iran, and he has an extensive background in fatigue and mechanics, which he made a great presentation back in September of 2019 at the LSP days that were hosted by both Zal and, we got an echo here. So did we get rid of it?
Yep.
Okay, sorry about that. So Dr. Keller provided a presentation on the some of the work that he had done at the time relative to the crack growth and laser peening. He's added to that, and he's going to give us a bit of an update on some of that work. And so with that, look forward to hearing from your presentation. Dr. Sören Keller, it's open to you to make your presentation. Thank you.
Yeah, thank you for the nice introduction, and thank you for the opportunity to present here today after such long time after our last laser peening meeting. So the topic is tailoring of laser shock peening introduced residual stresses to retard fatigue crack growth. And I know the introduction might be somehow clear for nearly everyone. However, I want to add this to put all of us on the same page, what I'm aiming at in this presentation and what this presentation is supposed to deliver. So we are talking about a damage tolerant design, and we want to apply laser shock peening to retard fatigue cracks. This is the overall topic. So what we need is, we need to control the fatigue crack growth to apply such a damage tolerant design. And the idea is to use the concept of residual stresses. And therefore, just a short explanation. So when we have a fatigue crack and we introduce compressive residual stresses in the critical areas of fatigue, then the idea is that these stresses reduce fatigue crack driving quantities and therefore slow the fatigue crack down. So when we have a present crack in a structure, I'm not that good in drawing airplanes, therefore I always use these CT specimen, and we have such a fatigue crack and we know the position of the crack tip, then we could introduce compressive residual stresses directly at this position, and this will reduce the range of the stress intensity factors and thereby reducing the fatigue crack growth rate. However, we always introduce tensile residual stresses as well. And these tensile residual stresses are very crucial. So we need to make sure that they are not in areas which are critical to fatigue. And so what's needed to apply such a residual stress-based life extension approach is, at first, we need reliable fatigue crack growth predictions, and we need precise calculations of the overall residual stress field. Now with this talk, I want to explain how we can set up a holistic simulation chain from laser shock peening process simulation to calculate residual stresses in the overall residual stress field, and then to predict the fatigue crack growth in these introduced residual stress fields. And in a second part of this presentation, I want to explain how we can tailor residual stresses to reach a certain level which might be needed to cause fatigue crack growth retardation. And this is done by prestresses. So what do I mean by a holistic approach? At first, I think it's important to have the stress, residual stress generation and the fatigue crack growth prediction in one simulational chain, because we need to know the overall residual stress field. So I want to combine the stress generation, and based on this, stepwise, I want to calculate the fatigue crack growth. I do not want to split it into fatigue crack growth prediction and residual stress prediction. And as a second, talking about a holistic approach, I want to combine experiments and simulation, where the simulation can explain us how the mechanisms are in physics, which we may not see directly, for example, the shockwave propagation or mechanisms during the fatigue crack growth. And the other way around, the experiments validate the simulation, and of course, they define the assumptions we can do in our simulations. So therefore, I want to have a close connection of the simulation and the experiments. Here, I want to talk about the simulation, and there I have 4 steps to calculate the fatigue crack growth rate. The first is the laser shock peening process simulation. Thereafter, I take the plastic strains from this process simulation and put this into a larger area, here the CT specimen, to calculate the overall residual stress field in such a large area. However, this area could be larger, so we could extend this to a compound instead of the CT specimen quite easily. And finally, I want to calculate the fatigue rate growth rate based on the stress intensity factors of fracture mechanics. So starting with the laser shock peening process simulation, here the idea is to reduce the peening patch to be simulated as much as possible. And here I want to calculate plastic strains in an area where I assume periodicity. So the idea is that I simulate a small peening patch and say that the plastic strains in the center of the small peening patch do not change when I would increase the peening patch. This is a strong assumption, but this can be proven if this is true or not. And in this case, of course, it's proven that it's true. So we can apply this assumption of this periodic plastic strains. I come back to this in one slide. There are many challenges of laser shock peening process simulation. So at first, the material behavior is not that clear at high strain rates. Here in this case, I assumed the simplest model possible, which is the Johnson-Cook material model, and it was sufficient. The second is the plasma pressure. This is very difficult to simulate or measure as well. So this is definitely a challenge of laser shock peening process simulations. And of course, the computational effort is important. However, by assuming periodicity, we are reducing this computational effort, and I will explain the benefits of the method I am going to propose here. So what I did is the idea of plasma pressure identification. So I take material properties from the literature, and then I adjust the plasma pressure that I match residual stresses, which are determined in experiments. And I do this for one experiment, and then I can apply this adjusted plasma pressure to different patterns or materials. And when I have an identification in the first case, then I have the real predictions for every following simulation where I change the pattern and the material and so on. So this is the idea of laser shock peening process simulation I applied. So when I have this laser shock peening process simulation, and this is able to calculate the residual stresses of certain specimen geometries, and what I'm aiming at are the plastic strains caused by laser shock peening, then I want to apply these plastic strains to a larger area, as I explained. So the idea is here to make use of this periodicity assumption. So I take the centered area, for example, here labeled with 110, and apply this to the larger centered area of the larger peening patch, here labeled with 110 as well. And of course, the edges are the edges, and the corners will stay in the corners. So I can build a large peening patch here for the CT specimen where I model just the half of it. And then here in this case, I simulated double-sided laser shock peening where I repeated the sequences twice from both sides. So I have in total 4 LSP treatments, and then the material is different for the plasma pressure identification. And then I can calculate the residual stresses in the CT specimen by transferring the plastic strains. In the CT specimen, these plastic strains are introduced as thermal strains, and then the temperature is raised about a certain amount of the CT specimen. Then I get the residual stress distribution, and I compare this to experiments, and I see I have a very good agreement. And what's important here, that this simulation chain I applied here did not had any further fitting procedures of PET material. So I just used the plasma pressure identified for another material with a different peening pattern, and the material properties from the literature, of course, and then I get a very good agreement of the prediction of the residual stresses. And what's the outcome is, I was able to reduce the number of laser shots, which is more than 500, to just 36. So this is what I gain in terms of the computational effort, which is dramatically reduced here. What I have is a CT specimen where I can calculate the residual stresses. So I model the half of the CT specimen, and in the symmetry line, I apply symmetry boundary conditions. And when the crack growth, then I replace the symmetry boundary conditions with contact conditions, which simulates crack face contact. And now I can calculate the residual stresses in the specimen, as I explained, by raising the temperature and having the thermal strains, and I get the residual stress distribution, which agrees with the experiment, which looks like that when I look on the symmetry plane. And I see that I have compression next to the surfaces which are peened, then I have a tensile area in the center, and then compression again on the other surface. And this is chosen purposely. So I wanted to have tensile stresses in the center to have a quite complex profile. Of course, this is applicable for pure compressive stresses through the surface, through the specimen thickness as well. And then I can calculate the local stress intensity factors shown here. And then I need to further reduce the stress intensity factor to just one average stress intensity factor over the whole thickness, which is shown here. And then I can calculate this stress intensity factor, the average stress intensity factor over thickness for every crack length at minimum load and maximum load. For a comparison, these are the stress intensity factors for an unpeen specimen, and I can see that there's a significant influence of the residual stresses. So, and this is the graph I explained in the slide before. What I need is two quantities, which are the crack driving quantities, where I can calculate the fatigue crack growth rate from. And the first is the stress intensity factor range, the maximum minus the minimum stress intensity factor at first for the base material. And here you see the difference of a peen specimen, where this stress intensity factor range is reduced in the peen area. And the second quantity is the stress intensity factor ratio. At first for the unpeen specimen, where you see that this is constant over the whole crack length. This is because I use constant amplitude loading during the fatigue testing. And here for the peen specimen, where I see an increased stress intensity factor ratio in front of the peening patch. And then I can calculate the stress intensity factor rate with the NASCO equation, where I don't need the last two terms because we are not in the fracture toughness or threshold regime. And then I can calculate, so these are the inputs, the stress intensity factor range and ratio as calculated in the slide before. And then I have the material constants C and N, and these are identified by base material, so not peen material. This is important. And then I can use these inputs and the material property parameters which are identified and calculate the fatigue crack growth rate. And I see this matches very well the fatigue crack growth rate measured for peen specimens. So at this point, I have a validated, or I have a good agreement of my predictions or calculations from the simulational chain and the reality, which are the experiments. So I want to further validate this method and make sure that I capture all relevant effects for the fatigue crack growth during in laser shock peening introduced residual stress fields. So at first, what I have is I have the simulational chain, which gives me the fatigue crack growth rate, and I have independently the experimental chain, which also gives me the fatigue crack growth rate, and they agree, so I'm on a good track. So for further validation, I use stress intensity factors that are calculated for a peen specimen with residual stresses with a numerical approach, and I take a specimen from the experiments, which is not peened. And then I apply this calculated stress intensity factors of a peen specimen calculated by the numerical approach to the real experiment of an unpeened specimen. And this simulates the effect which residual stresses have on stress intensity factors. And then I get the fatigue crack growth rate as well. And this experiment is named experimental simulation here. And when I compare all of these fatigue crack growth rates, then I see a good agreement of the simulation, of the experiment, and the experimental simulation. And that this proves that this approach takes all important mechanisms into account, which are, so this means that we can explain the fatigue crack growth rate based on macroscopic residual stresses alone. So possible changes of the microstructure are not important for this macroscopic, for this long crack behavior here. So, and then I can use this simulation to explain the mechanisms behind the fatigue crack growth retardation and acceleration, because when I'm in front of the peening patch, there are balancing tensile stresses, and they cause an acceleration of the fatigue crack. And this is due to stress intensity factor superposition, which means that the stress intensity factor ratio is increased, as shown some slides before. And when I'm in the retardation area, then I get crack closure effects, which reduce the stress intensity factor range. And this leads to a decreased fatigue crack growth rate. And this can be depicted by this stress intensity factor versus applied load graphs. So at first, I have the unpeened specimen, the blue circles, where this is a straight line when I'm in front of the peening patch where tensile residual stresses are present. And in an unpeened case, I don't have any residual stresses here. So I have a straight line, and a certain stress intensity, certain force, applied force causes a certain stress intensity factor. And when I apply a force range, then I get a certain stress intensity factor range, and this range doesn't change depending on the level of the loads. And when I have
remaining.
Okay, and when I have the pin case with the tensile residual stresses, then I see that this level is just increased. However, when I have crack closure, then I see that I have a certain stress intensity factor range where the crack is completely opened. However, this range of the stress intensity factors decreases when I'm in the area where crack closure occurs, and this really causes the retardation of the fatigue crack. So let's summarize. At first, we need to apply laser sharpening in a way that the residual stresses cause crack closure. Secondly, we need to pin as close as possible to the initial crack tip. This can be explained by the balancing tensile residual stresses in front of the pinning patch. Here I'm pinning with a distance to the initial crack tip. So the pinning even causes this shorter fatigue life. However, when I shift the pinning patch to the initial crack tip, then I get a real significant increase of the fatigue life. And secondly, I need to retard the fatigue crack in a region where the crack is the slowest. So this is automatically done when I shift the pinning patch to the initial crack front, because there the crack has the slowest fatigue growth rate. And all of these, what I explained here, was transferred to different material alloys and different laser sharpening systems. So this multi-step simulation scheme is transferable to different systems and materials. So we are, so this validates the general approach we choosing here. So in the second part, I want to explain the tailoring of residual stresses by pre-stresses. What we did is we introduced pre-stresses to a specimen by a 4-point bending. Thereafter, we applied laser sharpening on this pre-stress material. Then we release the pre-stress, and then we can measure the residual stresses. And when I do so, then I see that this pre-stresses during laser sharpening affect the resulting residual stresses here, mostly parallel to the pre-stress direction, and importantly, so if I apply tensile pre-stresses, I get higher compressive residual stresses. This is the main outcome. And then we modified the model from Hu to draw these residual stress versus pre-stress curve, and then we can identify a region where this relation between pre-stress and resulting residual stresses is linear, and we can make use of this linear region to tailor residual stresses quite precisely. And here's the use case for it. So we have a non-equibiaxial residual stress field. This is just a use case to demonstrate the tailoring. So if this is important to have an equibiaxial residual stress field or not, this depends on the use case, of course. This is just for as showcase. And then we get the non-equibiaxiality here of the residual stress profiles. Then in the first step, we need to calculate this non-equibiaxiality. Then we need to calculate in an experiment, figure out the second point. Then we can find this linear relation and choose the point where this non-equibiaxiality is 0. Then we can apply this to experiments, and we get this equibiaxial residual stress field. And this is showcase how we can apply these pre-stresses to tailor residual stresses. And of course, this enables, so it's possible to get certain residual stresses with a lower energy of the laser system, or we can treat materials with a higher yield stress more efficiently by pre-stressing the specimen. And this leads to the summary of this talk. So at first, I showed you a holistic approach, a multi-step simulation for the laser sharpening process to the fatigue crack growth prediction with this validated. Secondly, we were able to transfer the results and the simulation, multi-step simulation, to different materials and a different laser system. And finally, I showed residual stress tailoring by pre-stresses using this 4-point bending here as use case. With this, I want to thank you for your attention.
Great, thank you, Dr. Keller.